teenager, we all know the object-oriented programming is now the dominant programming paradigm and has significantly changed the field of software engineering. And today, we are honored to have a speaker, Barbara Liskov, who has won Turing Award for her contributions to the development of object-oriented programming. Professor Liskov now is an institute professor at the MIT's ECS department. He has developed two languages, CLU and Argus, that later led to the development of object-oriented programming languages. And Professor Liskov is also the first woman that was awarded PhD in computer science. So today she's here to talk about the power of abstraction. Yeah.
Thank you. Okay, so it's a great honor to win something like the Turing Award. And one of the things that it did to me was cause me to go back and reflect on what had happened and how I managed to develop the ideas that led to the award. And so that's what I'm going to talk about today. I'm going to first of all talk about the work that went on that led to this idea of abstract data types, which was the main reason that I got the Turing Award. Then I'm going to talk about CLU, which was the language I developed to explore that idea. I'll make a few remarks about some work I did on type hierarchy, and then I'll conclude. So I'm going to start with some prehistory. So I got my PhD from Stanford, and what you may not know is that I did my work in AI. My PhD thesis was on a program to play chess endgames. And I knew sort of halfway through my time at Stanford that I actually wanted to move out of AI into systems. I decided to stick with AI to get my PhD because after all, that's the main point of getting a PhD, is to finish and go on and do something else. But when I left, I went to work at the MITRE Corporation, and I switched from AI into systems. And the first project I worked on there was to design something called the Venus machine, and this was a machine architecture. What was going on at that time was that people were using something called microprogramming. So this is the Interdata 3. This is the machine on which I developed the Venus machine. And this microprogramming was really basically something that was a lot like a RISC machine. So as I recall, the Interdata 3 had an instruction set consisting of 16 instructions. And very much like what you would have on a RISC processor. It came equipped with read-only memory. I believe there were 16K words of read-only memory, but I can't remember for sure. It had a teletype, a tape reader, and a console. So it was a pretty primitive machine. And the idea was that you would take a machine like this, and you would use those low-level instructions to develop a more usable instruction set that the people would really write programs in. Now, later on, it turned out that we were actually fairly happy using RISC machines. So one of the interesting questions is, why did people think that that low-level instruction set wasn't sufficient in itself? And I think the answer was, actually, some of the machines were pretty Baroque at that time, so there was a sort of an idea that machines ought to have complicated instruction sets. But another point is that people wrote a lot of programs in machine language in those days. And I think one of the reasons that we can live with a RISC architecture is that it's actually the compiler generating the code rather than people writing that code. It would be very tedious to have to write many sequences of instructions in order to do simple things. Okay, so I developed the Venus machine on the Interdata 3, and the most interesting thing about that instruction set, which I've mostly entirely forgotten about, was that I took semaphores, this idea of Dijkstra's that he talked about in his famous paper on the THE operating system, and put them into the hardware. So other than that, that was a pretty vanilla system. And then, of course, what happens when you develop something like the Venus machine is the next question that arises is, well, what's it good for? Is it good for anything? And so to answer that question, I developed the Venus operating system. And this is pretty early days. This is around 1968 or 69. And the Venus operating system was a small time-sharing system. It supported 16 concurrent users. And it was a good target test case for this machine because I could take advantage of the semaphores for all the process scheduling and so forth that needs to happen in an operating system. So I finished working on the Venus system sometime around sometime in 1970 probably. And at that point, I started to work on programming methodology. So what happened was there was a software crisis. Now, that probably doesn't seem too astounding to you because there's always been a software crisis. There's still a software crisis. But maybe the software crisis was a little new at that point. People were coming to realize that what we wanted to produce in software was beyond our abilities. We really didn't understand how to produce software very well. We were very ambitious about what we wanted to do in software. Another thing that happened at that time was that the machines tended to be underbought. You know, machines were a real cost. You had to go out and spend money, and they were pretty expensive in those days. And so it wasn't unusual for a project to decide to try and save on the hardware by taking it out of the software. The software costs were not real. You know, you just couldn't figure out how much it was going to cost to build the software. So not only were we building systems that were sort of more than we could manage, but we were doing them on machines that weren't powerful enough, and so that added a whole other dimension to the problem. So the government was very worried about this, and MITRE is a corporation that does a lot of work for government research, and they asked MITRE to look into this question of how can we get control of this software crisis. And so I started to work on this project. And programming methodology is actually about two related but different topics. First of all, there's the question of how should programs be designed. You know, what's a good design methodology for coming up with an implementation structure that's going to actually solve the problem that you're interested in solving? And the second problem is how should those end products be structured? What kind of organization makes sense for them? So what I'm going to do now is I'm going to talk about some of the literature that existed at that time. So I read a whole bunch of papers. So I went out, what I came in with was, I'd done all this work on Venus and all the stuff I'd done before, and I went out and I read the literature. And I'm going to talk about a few of the papers that I read. I'm sure that some of you in the audience have already read these papers, but I suspect that many of you have not, and I recommend them. I'm not trying to say these are the only good papers, but this is a set of good papers, and I do think as a field in computer science we don't pay enough attention to the past, and we have a tendency not to know what went before, and it's a good idea to know what went before. Okay, so here's the landscape as it existed at that time. The first paper I want to talk about is this paper of Dijkstra's called Go-To Statement Considered Harmful. Okay, now this was a very controversial paper. And this may seem surprising to you because today the battle in some sense is over. The go-to statement is gone. You know, it doesn't arise in the programming languages that we're familiar with. But at the time, it was an important part of programming languages like Fortran, for example. And there was a lot of resistance to this particular paper. What Dijkstra said in his paper was that when we reason about a program, we are looking at the program text, which is a static description of what's going to happen. But we're actually reasoning about the program when it runs. And so therefore, in order to make the reasoning process work better, it would be good if the static structure was very closely related to the dynamic structure. And when you have a go-to statement, you're sort of jumping around and there isn't that very close correlation. And then he talked about debugging as an example of how you can get into trouble with the go-to statement. If you think about debugging, you're at a particular point in your program and you're trying to figure out what went wrong. And in order to answer that question, you need to know how you got there. And if you're using a program with well-structured control structures, the answer to that question is pretty easy to get at. But if there are go-to statements, you could have come from anywhere. And I should say as an aside that prior to my work, prior to getting my PhD, I maintained a huge program written in machine language that had non-reentrant code, where the program actually modified itself in order to take, save one instruction. It would stick a little branch statement over on top of something else because it knew that it was going to take that branch later on. So I had a lot of sympathy with getting rid of go-tos. Go-tos are minor compared to what I just described. Okay, why was there so much controversy? Well, I think that partly it was just that people we're used to doing things in a particular way. And of course, you can write good programs that have gotos in them, but Dijkstra admitted that. I think also, though, that the programming languages that existed at that time didn't have adequate control structures in them. So if you think about the use of gotos in some of these old programming languages, you can see that they were used for very good reasons. For example, if you don't have an exception mechanism in your program, your programming language, then passing a label as an argument to a procedure gives you a way of jumping to the handler and getting it out of the normal flow of control. Or if you don't have a case statement in your programming language, then using a table of labels is a very good way to simulate a case statement, which is a valuable programming construct. So I think that the arguments against were to some extent, justified based on the weakness of the control structures in the programming languages. Okay, the next paper is this excellent paper by Nicholas Weert on program development by stepwise refinement. This is a paper that's about the design process, and specifically it's about top-down design. So Weert says you start with your program statement, and you make one design decision. And this gives you a certain structure to your program, and after you've made that one design decision, you take some of those things that are left. These are like statements in an abstract language where the language doesn't really exist, and so you couldn't run it. And you sort of pick up one or more of those statements, and then you figure out what to do with them. And you proceed in this very orderly way, one decision at a time. The program that he used here was the 8 Queens problem. And his first design decision was that we'll get a solution that has one column in it. And when we're happy with that, we'll go to the second column. And if we have to backtrack, we'll backtrack. So that's a sort of an example. I would say that Weert was not particularly interested in the program structure. He was interested more in the design process. And of course, we all know today that you can't entirely do top-down design. You have to also be informed by sort of bottom-up considerations where you take into account what's doable. But there's no doubt that a design process to a very large extent has to be top-down, because if we don't focus on what it is we're trying to provide, how can we possibly end up with a program that actually does what we want? Here's a very famous paper by Dave Parnas. This is one of 2, actually. Dave was actually more interested in program structure than he was in program design. And so what he says in this paper is that your end product has to have these things called modules. He says, I don't know what these modules are exactly, but they interact with one another. And it's very important to understand these interactions. And so there's this famous quote here: the connections between modules are the assumptions which the modules make about one another. And what he's pointing out there is that the connections had better be small, because if you're going to understand things, the simpler the better. And there can be lots of connections. They may not be direct, this one branches to there. There could be a lot of connections in data as well. Okay, now as a result of these papers and a whole bunch of others I haven't talked about, and also my work on the Venus system, what happened was I realized as I was doing all this reading that I'd actually been using a methodology in the design of Venus. And the methodology was based on something called partitions, and I wrote this up in this paper that was published in 1972. And here's what a partition is. It's a module. It has a whole bunch of stuff hidden inside it. And it provides an interface consisting of a bunch of operations. And the idea is that you can only communicate or only get access to the stuff that's hidden inside by making calls on these operations. And Venus was, the design of Venus was unusual maybe in that the whole system was organized this way. It was very common at that time instead for programs to all communicate through some global storage. And so what's happening here is rather than having global storage and everybody uses it, instead I divided that storage up, I stuck each bit of it into some different partition and had this very orderly way of the partitions interacting with one another. So that was what was described in this paper. Okay, now, so I had produced this paper on partitions, and at this point I moved from MITRE to MIT. So in the fall of 1971 I started at MIT. And I was an assistant professor, and I was learning how to teach courses that I had no background in and stuff like that. sort of common stuff for an assistant professor, perhaps. But as far as research was concerned, I was really, really interested in programming methodology. I should say, by the way, that it's not surprising that my background was in systems at this point, because if you think about operating systems, at the very least, there's a very clean separation between the user code and the systems code. If you didn't have a very strong boundary there, of course you would have no way of guaranteeing that the system does what it's supposed to do, and so that probably did color my thinking. Anyway, I was really interested in programming methodology, and the problem that I was focused on was how can these ideas be used to build programs. What I felt was you could read these papers, they seemed to make a lot of sense when you read them, but then when you tried to apply the ideas to a program of your own, it was really unclear what to do. And I'm thinking particularly here about the ideas of Parnas and my own ideas about partitions. So I had these ideas about modularity, but I just didn't know how to convey these ideas to people. And so I thought and thought and thought about this, and sometime during the fall of 1972, I made this connection between partitions and abstract data types. And in retrospect, it seems like it was clear that there was this connection. And you sort of look at the work of Parnas and you can say, yeah, he was talking about modules and there were resources inside, so that was another thing that was sort of clear. But of course, it wasn't clear at the time. And another point, but I have no idea where the idea came from. So it was there waiting to be discovered. Okay, this is very common when you make an advance like this. There's something sitting there, it's waiting to be discovered. It isn't uncommon if more than one person discovers it at about the same time. I was thinking about it a lot, and then one day, there it was. Okay, so that was in the fall of 1972. In the spring of 1972, there was this SIGPlan SIGOPT interface meeting, and this was a meeting that was ostensibly about programming languages in which to implement systems. However, the meeting itself was actually mostly about programming methodology, and so that was sort of the topic that was being discussed. And I gave a talk on my ideas about abstract data types, and Steve Zillis, who was a graduate student at MIT, had a paper there that talked about very similar ideas. So Steve was an unusual graduate student. He worked for IBM. He was older, and IBM was allowing him to pursue his thesis sort of part-time. And so he'd been thinking a lot about programming. So Steve and I had similar ideas, and so we started to work together. So now I'm going to tell you what we did. Okay, so here's some more landscape. So Steve and I, between us, were very knowledgeable about programming languages. Steve came from IBM. He knew all the languages that IBM was producing. There was Fortran, there was PL1, he knew BASIC. I had done all that work in Lisp, and because that Lisp was the language you used to do work in AI. And in addition, we knew about what was going on in programming languages in general. That was the time of the ALGOL languages, and that was what you might call the academic stream of languages. And so we were familiar with all the work that was going on in programming languages. So I'm going to talk about a few papers again. First of all, you may not know that there was a time when people talked a lot about what were called extensible languages. So the idea was that when you design a programming language, this is always a problem when you design a programming language, you take away expressive power because you provide this language and underneath it is, say, the machine language that you use to implement it. And there are things that somebody could have done if they had had access to that machine language that they aren't going to be able to do using your programming language. There was a lot of worry about this. There was a lot of talk at the time about universal programming languages and whether these could ever work and so forth. I mean, obviously we can see now they do work. But there was a lot of worry that by designing a programming language and having people use it, you were taking something away from them, and this was bad. And so extensible languages were an attempt to give it back. And this first paper by Steve Schumann and Pierre Girand is a survey paper that talked about the state of the art in extensible languages at this point in time. And what they pointed out in that paper was that there were two different kinds of research that were going on. First of all, there was what they called syntactic extensibility. And the idea here was that, I've got a program and I'm using factorial in it. Why can't I have the exclamation point and use that whenever I want to call the factorial program. And they actually talked about, letting users specify syntax in B and F, and then, as a result of this, the compiler would now be compiling a different language than it compiled before. In general, this is a really bad idea. And the reason it's a bad idea is because we know today that program readability is much more important than program writability. That was not so clear at the time. At the time, there was a lot of focus on let's make programs really easy to write, and less of an understanding that not just reading, but understanding is what really matters. Programs are read many more times than they're written, and it's very important that you use a standard syntax so that at least the reader doesn't have to contend with trying to figure out what your syntax means. I mean, of course, you could use these tools in a good way. You could define a sort of a special domain language that's used by a whole category of users and that's specialized for that domain. But in general, you would not want every programmer who came along deciding to change the syntax a little because it made it a little easier for what they were doing. The other thing that Steve Schumann and Pierre Durand talked about was semantic extensions. And what they meant by this basically was type definitions. So you could say foo equals array of int, something like that. That's kind of a semantic extension, except they meant a little more than that. And Bob Balzer's thesis talks about one example of what they were talking about. What he says in his thesis is, I'd like to have data types, and each of these data types is going to have 4 operations. So he's thinking about data types as always being collections. And the operations are, you can add something to collection, you can take something out of a collection, you can access something in the collection, or modify something in the collection. So the 4 obvious things. So in a way, it's kind of like a straitjacket. Every data type has to fit into this format, but the idea of having a data type with a set of operations with it, you can see coming out of this work. However, there was no encapsulation in this. So it was just, and furthermore, there was syntax. So you could say, assign S to X, and this would mean pop, because S was a stack and X was the thing that was coming out of the stack. Okay. Here's a paper on Simulus 67. This is a very a good book to have in your library. This is what we used to refer to as the little black book. It's a book that has 3 important papers in it. This is one of them by Dahl and Hoare about Simulus 67. There's a paper by Dijkstra on effectively top-down design, and a paper by Tony Hoare about data structures. And it's a sort of a classic. Okay? Simulus 67 was a very interesting language. It was definitely ahead of its time, and it's a precursor of Smalltalk and the following object-oriented programming languages. It had a mechanism, a class mechanism, where you could define some data structures and a bunch of operations that executed on those data structures, and then you could have a subclass where you sort of took that code and you extended it to provide more functionality. So it's very much related to the object-oriented school of programming. It didn't have any encapsulation. So in that sense, it didn't provide what I thought was the most important thing that you wanted for abstract data types. Here's a very important paper by Jim Morris. This is one of 2. Jim was very interested in modularity, the way that Dave Parnas was. And what he says in this paper is that it's very important when you have your modular program structure that you be able to reason about each module in isolation. I mean, this is a key idea that underlines the whole reason why modularity is a good idea. If you have to be able to think about each module separately and not have to worry that something's going on somewhere else in the program that makes your reasoning invalid. And then Jim went on to point out that there were 2 things you had to watch out for that would make modularity not work. The first thing would be if there was a way for code outside the module to get inside the module and modify stuff. Okay? And the second thing was if there was a way for code on the outside to fake it, to produce what appears to be an instance of the module and somehow get the module to operate on it, because then you can't expect that the module is going to behave properly. And actually, this paper was a very early, sort of ahead of its time paper. He talked about very important ideas in how you reason about data abstractions, because he was talking about representation and variance. You know, what kind of, if you think about the data structures that are inside the module, what kinds of predicates are true for all instances of the module. And he was also talking a bit about abstraction functions, how you relate the inside to the outside. He then went on to talk about, well, how do I get protection? Because, you know, we're talking about enforcing this. And his idea was to have two operators, seal and unseal. So the idea is when data came from the module, you'd seal it up. And think about it as encryption. You'd encrypt it with a key that only the module knew. And then when it came back in again, the module would decrypt it, and only if it decrypted successfully would it be. So this way, encrypting protects it, and decrypting guarantees that you can't be faking it. Okay, finally, there's this paper by Bill Wolfe and Mary Shaw, Global Variable Considered Harmful, and you can see that this name comes from Dijkstra's paper, and it was structured sort of like Dijkstra's paper. So what they're talking about there is, you know, Algo introduced this notion of block structure. And block structure was a good idea and a bad idea. It was a good idea because as you go into an inner block, you can have definitions in there that stuff on the outside of the block can't get at. So it gives you a kind of locality and modularity. It protects that region from stuff on the outside. But it was a bad idea because it also had this notion that stuff on the outside was accessible everywhere. And so there was this notion of sort of global scope. And what they were talking about is that global scope is not so great because you have all these programs that communicate through those global variables, and these add a whole bunch of extra connections, and they make it much harder to figure out what that module is actually doing. You have to put this in the context of the time and think about it from the point of view of the academic stream of languages, which were all focused on block structure and which seem to have the idea that your entire program ought to be one big block, you know, with global sort of on the outside and then these inner scopes and inner scopes. Okay, so Steve and I read all these papers, and we worked intensively over that maybe 6-month period. And what I remember is the summer of 1973, where as far as I can remember it never rained, because Steve and I had lunch outdoors every day. There was a lovely outdoor space near the building where I worked with trees and benches, and we used to meet for lunch every day, and we'd be talking about, you know, our ideas and how we'd advance them in the period in between. And by the end of the summer, we had written this paper about abstract data types, which was actually published in April of 1974. Now, what was in this paper was, first of all, it talked specifically about what is an abstract data type. And it made the point that an abstract data type has objects, but it also has operations, and the operations are the only way you can access the objects. So there's complete encapsulation. Only the operations themselves can get inside. And it also made the point that whatever the set of operations is, it's going to be specific to the type that's being defined. So there's no idea that there's some predefined set of operations as there was in Bob Balzer's work. Instead, whatever this type is, you define the operations that make sense for it. In addition, the paper proposed a programming language, so in a sketch. So it talked about a way to implement abstract data types. It said that we ought to have polymorphism. In other words, it's not going to be enough to define set of integers as a type. We're going to want to define set, where there could be a set of integers, a set of reals, and so forth. It also said we'd like to have static type checking, but we weren't sure we could manage it, and the reason we were unsure was because of the polymorphism. And it should have an exception handling mechanism. So now what I'm going to do is I'm going to talk about how I went from abstract data types to CLU. So here we are now in the fall of 1973, and it may seem like I was already sort of working on CLU because I just talked about a paper that had stuff in it, but in fact it was a decision to go forward and take this next step of turning those sketchy ideas into something real. Now, what happened in 1973 is that 3 new graduate students arrived at MIT and decided they wanted to work with me. And these 3 graduate students, Russ Atkinson, Craig Shepard, and Alan Snyder, were, along with me, the real designers of CLU. By now, Steve had moved off, and he was coming to all our design meetings, but he wasn't working on CLU. He was working on his PhD thesis, which was about algebraic specifications of abstract data types. And there was also a large group of people who came to our meetings. The whole of Jack Dennis's Dataflow group used to come to our meetings, but the real work was done by the 4 of us. I would have loved to have shown you some pictures of these people, but I don't have them at that time, and I don't think it's too interesting to show what they look like today. This is a picture of me with Jack Dennis in about 1973 or 4. And Jack Dennis, as I mentioned, was one of the people who used to come to the group meetings. Okay, so I had very specific reasons why I decided to design a programming language, and they're pretty compelling when you think about it. The first one is that programmers think about programs in terms of programming languages. So programming languages are a very good way to convey ideas to programmers because they are the thing we work with. The second point was, if you put ideas into a programming language and say, okay, build your programs in this programming language, you'll be able to find out whether these ideas really work or not. The third thing is that programming languages are mathematical objects. They are precisely defined. Now, mind you, at that time, they weren't all that precisely defined because, in fact, the compiler was the definition, and the next compiler might define things a little bit differently. These were the days before operational semantics came along, so people were struggling at that point with how would you specify a programming language. Nevertheless, we tried, even though we didn't have any formal tools available, to come up with a very careful, precise definition of the language. And this was very important because a lot of the work in the literature was very mushy. They had these ideas that kind of waved their hands a bit, and they never quite got down to exactly what the rules were. And so by putting stuff into a programming language, it meant we had to make the rules precise. And then the final question was, performance is very important, and we're going to have to implement this language, and we have to think about whether the features that we're coming up with can be implemented in such a way that they perform well. Okay, so we're doing language design. Language design is really hard. And actually, it's akin to interface design. So interface design is also not so easy. And I think sometimes people don't think carefully enough about their interface design because, in fact, you ought to think about it as a programming language. It may not have so much syntax, but it does control everything that your users can do. And so these principles at the top apply to interface design just as much as they apply to a programming language. It has to be expressive enough. They have to be able to do easily the things that they really need to do. But it better be simple and easy to use, because otherwise they'll be confused about it and they won't find it nice to use. And of course it has to have adequate performance. It doesn't have to have super duper performance. People get very confused about that, but it has to have performance that's good enough that it matches whatever it is that you're trying to provide. Okay? In addition to these goals, which are for every programming language, we had a few others. We wanted minimality, by which we meant we wanted to put in just the set of features we thought we could get by with and nothing more, because we were kind of looking for that minimal sort of design point. By uniformity, we meant that whatever was built into the language ought to apply to the abstraction mechanisms as well. And that was primarily polymorphism. And then by safety, we meant we'd like the language compiler and runtime to find as many errors as possible so that to make the job of producing correct programs easier. We also had some restrictions. The first one, no concurrency, was not there going in. I originally did think that CLU would be a language in which you could write parallel programs, but I threw that out pretty early on, and that was a very important decision because when you're designing, because it allowed me to focus on the main point of the project without getting distracted by concurrency, which is a difficult problem in its own right. It had no go-tos, that's coming directly from Dijkstra. It had no inheritance because that was not the point. The point was encapsulation, data abstraction. It was not an inheritance mechanism. And in fact, I was paying very little attention to inheritance, and the work on Smalltalk was more or less contemporaneous, and I didn't even know anything about it till around 1975. There were some assumptions and decisions that got made almost without noticing, and here what you mostly see is my Lisp background. So I'd written lots of code in Lisp. So I really was going away from the Algol school here. You know, Algol says your program is one big block, and they were very concerned about pointers, and the heap was something considered dangerous. But Lisp is a heap-based language with garbage collection, and that was a decision that we made early on, and it was a very important decision. And the reason it's important is because if you want to do separate compilation, where here I have a program that uses a data type, here I have a program that implements it, and if you'd like to be able to do that in a way that allows you, for example, to not have to recompile the using code if I choose a different way of representing the data abstraction, then if you put that stuff on the stack, you're going to have trouble because you need to know how much space to reserve on the stack. But if I put it in the heap, no problem. So it was really an important decision. And an interesting point is that the work that Bill Wolf and Mary Shaw did on Alphard, which was another data abstraction language developed at about the same time, they went to the stack direction, and I think it gave them a lot of trouble and added more problems that we were able to sidestep. It had no block structure. I mean, it did have block structure inside the modules, but it was not, you know, the one big program with block structure. Instead, it was a separate compilation program like the kinds of stuff you see today. And that, again, is coming from Lisp. If you think about Lisp, you know, you write this procedure, you write that procedure, you just keep adding to your program, except this was a compiled language rather than an interpreted language. However, where it deviated significantly from Lisp is that it had static type checking. And this was also based on my experience in Lisp, because I used to get so annoyed when I was working on my thesis at these errors in my program that a little static analysis would have gotten rid of. Okay, so what I'm going to do now is talk a bit about CLU. And I'm just going to focus on the abstraction mechanisms. There was a lot of other stuff going on in CLU, but I'm not going to talk about that. Okay, so clusters are what we had to implement abstract data types. And the most interesting thing on this slide is the top line, because there what you see is a list of operation names. So this is making that point that a data type provides a bunch of operations, and this is how you interact with their objects. So the interface of a cluster listed the operation names. What I've added to the slide now is a little code that uses a data type. And what's really interesting on this part is that $ notation. It's crufty, and I would not design it this way today, probably. But it's actually making a semantic point, and that is, in CLU, we thought of the operations as belonging to the data type rather than to the objects. So this is very different from the object-oriented languages where you say x dot, you know, push or whatever it is. Here we would think of push as belonging to stack, not to a particular stack object. And that notation is expressing it very directly. And the reason why we use the $ notation is because, of course, there could be many types that have operations with the same name, so you have to have some way of disambiguating what you're doing. Okay, here's a little bit of the implementation of a data type. And what's interesting on this slide is that rep equals line. This is like what you would do in Java, where you have a set of instance variables. So this is how we expressed the representation of the objects. Most often, the rep would be a record type, and it would have several fields. So, you know, instead of having array event, it might have been a record with a size field and then an elements field. And then finally, here's one of the operations. And what's interesting here is the use of that word CVT in the header. Okay, and what that is a sort of personification of Jim Morris's ideas of seal and unseal. This is seal. So the idea is that inside we have a rep object, an array. Outside we have an int set. And as we push out, we seal up the array and turn it into an int set. And CVT could also be used as an argument, and that was the unseal. Okay. However, unlike Jim Morris's paper, where he talked about implementing this not through encryption but through some sort of hidden key, this was all done through compile time analysis. Okay, here's polymorphism. So you can build not just an int set, but you could build a set, and the type would be the parameter. We didn't call these polymorphic in those days. We called these type generators because we thought of this as being a piece of code which, when given a parameter value, would produce a type. And actually, you can see on the bottom of the slide, when I say that set of int there, I'm in some sense invoking the set cluster to produce a set event, and that's a type. Okay? All right. Now, there's a problem, however, with polymorphic function sets, and it took us a long time to figure out a solution to this. The problem is that not every type makes sense as an argument. Okay? So if you think about sets, in order for there to be a legitimate parameter for sets, that type has to have an equality relation on it. Because when you stick something in a set, if you stick the same thing in again twice, if it goes in twice, it's only in there once. If you remove it, just once. Okay, so not all types have an equality relation. And so we just didn't know what to do with this for a long time, but finally we came up with a solution, and that was this where clause. So we added to the header of a parameterized cluster a where clause that told you for the parameter type what operations it had to have. And so here I'm saying it has to have an operation named equal, which takes in two t's and returns a Boolean. Okay, and then given this where clause, I can do compile time checking, because I can check when we instantiate that the type being put in as a parameter does have such an operation. And I also, inside when I compile the code of set, I can use that operation. And here's a place where I'm using it. I'm actually using it down there in that if e equals x of I. That's a little what we called syntactic sugar. So we provided a very minor way of taking a little convenient syntax and turning it into the longer form of calling the equal operation directly. Okay. All right, now I want to talk about exception handling. And exception handling then was not like it is today. There was a lot of confusion about exception handling, and it was very unclear what an exception handling mechanism ought to be. We did think exception handling was very important. And the reason it's important, it's still as important now as it ever was. It's because, first of all, you'd like to define, if possible, total functions that work over all the elements of their domain. Okay? But in addition, generally speaking, a function is not able to do the same thing for all elements of its domain. And when it has to do something different, you want a way of it bringing this to the attention of the caller. And so mushing it into a return value doesn't work very well because the caller can ignore that, and so forth. So you want an exception mechanism because that allows you to bring things to the attention of your caller. But it was sort of unclear how to do this. And John Goodenough wrote this paper in 1975 in which he talked about what is the state of the art with respect to exception handling. And he also proposed some notation. But what he said about the state of the art was that there were two key issues. First of all, should an exception mechanism be a termination mechanism or a resumption mechanism? So termination means you make a call to the procedure, it throws an exception and stops. That's the end of that procedure. Resumption means it throws up something, some other code handles it, and then when that's finished, control resumes in the procedure that threw the exception. And PL1 has a mechanism like that. In fact, PL1 has a mechanism where you could throw an exception, maybe you resume, maybe you don't. Okay? And then the other thing that was not clear, or that had many different techniques, was how do you specify the handlers? Today we think about them as being at the call site, or related to the call site through the program structure, but then they might have been defined off on the side. You might have said, for this module, here's the exception I want to handle, here's how I want to handle that exception, and so forth. Okay, so with this as a background, we settled on an exception mechanism that was a termination mechanism. Here's just a little code for the choose operation, which is an operation of set that returns an arbitrary element of the set. And obviously, if you pass this an empty set, it can't return an element. And so in that case, it signals empty. And that's the end of that call. And then here's a little handler. Okay, so we chose call site, as has become the norm today. So here I have a call, the choose operation, and I've attached an accept statement to it. Okay, so this probably all looks very familiar to you because this is how it's done today. There is one thing about the CLU mechanism, though, that isn't done today, and I actually think CLU did a better job than what's happening in languages today. If you think about what happens when an exception comes up from a procedure that you call, there are three possibilities. Okay, first of all, you might handle it. So I'm running through a loop, the exception happens, this means it's the end of the loop, I go on and do the next thing. Another thing that happens is you propagate it. So an exception at a lower level means that I also am going to have to terminate an exception, but the exception that I terminate in is different from what happened below. It's my exception. But there's a third possibility. It shouldn't happen. So for example, I just checked that the set was non-empty. Then I called choose. Well, you know, choose might throw an exception. And the real question here is, you know, what does the language design say you have to do about this? So if you think about Java, Java says you better write the code that handles the exception. You think about C#, C# says, you just let the exception go racing up. Okay, these are both not very good decisions. The first one is bad because you end up with all this useless exception handling code. And the second one is bad because now you never know what the interfaces of your modules are, since any old exception could come shooting up through them. What CLU did was something different. It had the failure exception. So what happened in the runtime was if an exception, or actually the compile time, if an exception should happen and it wasn't handled by the code of the caller, we actually changed it into the failure exception. And the failure exception had an argument, which was the name of the exception that caused the problem. And then the idea was every procedure had this one additional exception, failure. And this was typically treated in a very different way. You know, you would go back to some high level of your program where you had a checkpoint, you throw away everything and start over again. Okay? And the principles that guided us were, on the one hand, to have accurate interfaces, and on the other hand, to avoid all that useless code. Okay, the final topic here is iterators. So many, not all, but many data types are collection types. And whenever you collect stuff, it's probably because you wanted to do something with it. And typically what you want to do with it is iterate over it. I want to print all the elements in the set, or I want to add them together, or whatever it is that I want to do. So you have the need for a construct like that. And we simply had no idea how to do this. We had a couple of ideas that we could have used with the mechanisms we had available. For example, I could take the set apart. Maybe I have a select operation which returns an arbitrary element and takes it out of the set. That way I could iterate over the set using the select operation, but at the end, the set's empty. And sometimes I don't want to make the set empty, I'd like to use it further. Okay, or we could complicate the abstraction. I could turn the set into an ordered set with a notion of the first element, the second element, and so forth. But it's, in general, really a bad idea to take an abstraction and make it more complicated. So that was also not a very desirable solution. So what happened was, we went to visit the group at Carnegie Mellon. This is Bill Wolf and Mary Shaw, who were developing the Alphard language. And they described to us a mechanism they were developing called generators. And you can think here about Java generators. Okay, so the idea was that generator had several different operations, and one of them would return the next element, and one of them would tell you when you were finished, or something like that, and it was linked to a for statement. And we could see that this was a solution to our problem, except we thought it was sort of inelegant. And so on the plane ride home, Russ Atkinson, who was one of the students I mentioned before, invented iterators. And the basic idea in an iterator is it's like a procedure, except that it yields results. And so the idea here is I'm calling an iterator in my for statement. So members is an iterator. And when the for statement starts, I call members. And members is going to produce the elements of the set in some order. And so when it produces an element, then we run the body of the loop. And when we get to the end of that iteration, we go back into the iterator, which produces another element. And so we go back and forth like this until finally the iterator is finished, and that terminates the loop. So that's the basic idea of iterators. And here, just to sort of complete the story, is a little example of how you would implement members, and notice that it also is implemented using an iterator. So these iterators do not have full expressive power. So iterators are defined, they can be nested, they can be recursive, but they cannot be used to compare, say, two lists side by side. Supposing I wanted to check whether two lists side by side had the same elements. I could not do that with iterators. I could only look at one list at a time. And this was a conscious decision. Basically what we were going for here was what you might call the 90% solution, where we had a mechanism that was simple and easy to use and was mostly what you wanted. And then the idea was, well, if somebody wanted something more complicated, they could build it directly using data type, sort of a generator type solution. A final point is that this provided a very efficient implementation technique. What we did is we took the body of the loop, we turned it into a little procedure, and passed it as an argument to the iterator code. So you would call the iterator, which would call the loop body. And so that made a very efficient mechanism, whereas a more complex iterator mechanism requires basically a coroutine-like structure. The main thing to look at there is how easy it is to implement that iterator. And this is a pretty simple one, but walking over a list can be pretty hairy if you try to do it with generators. It's very straightforward with iterators. Okay, so that's it for CLU. Okay, so after CLU, what happened was, yes?
One thing I'm really curious about in CLU is, if you looked at all that code, there were no semicolons after any lines. When did you realize that that stuff wasn't necessary in these types of imperative languages?
So the question was, how come we have no semicolons? And the answer is it was a conscious decision. We decided to develop the grammar to get rid of the semicolon because they were so annoying in the languages at that time. You were always getting these errors, you know, did the semicolon go before the end, or maybe the semicolon couldn't go before the end. And those were sort of arcane rules, and so we just decided you can design a grammar that doesn't require semicolons.
Did you know that already?
It's somehow or other, I think we took it as something we wanted to do. And you know, I think we had to play around with the grammar a bit to make it work, but it just seemed like it was so silly to have these stupid syntactic errors that meant nothing. There's a lot of stuff I haven't talked about in CLU, and that's an example of one of the things I'm not covering. Okay, so after CLU, I actually moved into distributed computing, and when I developed the Argus language, that's a language that has concurrency in it, so it's like I put that concurrency problem aside, and then I picked it up later. But when I picked it up in Argus, by then the internet was beginning. It was actually the ARPANET. And so I picked it up in the context of distributed computing, and Argus is a language in which to build distributed applications. And I've been mostly working in distributed computing ever since, although I have made little steps into programming language design every now and then. It's not just Argus. I designed something called PolyJ, which was when I was very annoyed that Java didn't have polymorphism. So with my student Andrew Myers, we developed a polymorphic Java and so forth. The only thing I wanted to tell you about was one last thing that's related to this. Oh, and another point is I did continue to work on program methodology. I also was very interested in the question of how do you specify abstract data types? How do you reason about the correctness of abstract data types? So I did a lot of work in those areas. But I did want to talk a bit about type hierarchy. So what happened was in 1987 I was asked to give a keynote at UPSLA, and I decided that this would be a good time to visit object-oriented languages and find out what was going on with them. I hadn't been paying much attention to them, and so I read a lot of papers, and some of them were pretty bad, and some of them were okay. But what I discovered was that there was mass confusion. And the problem stemmed from the fact that inheritance mechanisms were being used for two purposes, and these two purposes have different needs. They were being used for implementation and also for type hierarchy. So implementation is just you have a class, and then you say, well, here's my class C, and C prime is a subclass, and then C prime sort of inherits all sorts of code from C. And the main thing, I don't personally think that implementation inheritance is actually very important. I just pointed out in the paper that it violates encapsulation because Smalltalk, which was the main object-oriented language at the time, had encapsulation in the sense that using code, could use objects and would not be able to get at the private fields, but that was not true of the subclasses. And so if you wanted to re-implement this class, that created a problem where you had to worry about those subclasses. On the other hand, I thought that type hierarchy was very interesting, but it wasn't very well understood. And I read papers in which people were clearly really confused about it. So, you know, there was a paper, I can't remember what paper this was, in which they talked about how stacks and queues could each be subtypes of one another because they chose, you know, an add method that added an element and a remove method that removed an element, and therefore, you know, they've got methods of the same name, they've got the same methods, and therefore each one could be a subtype of another. And yet clearly this is not true, because if you wrote a program that expected a stack and somebody gave you a queue, you'd be awfully surprised. Okay, so in this paper I wrote a simple statement that says objects of subtypes should behave like those of supertypes if used via supertype methods. So sort of the obvious intuition, if you think about it, you know, I write a program in terms of some supertype. I know what that supertype is supposed to behave like. I'm actually passed an object of a subtype. Well, that's fine. You know, I use it with the supertype methods. It just should behave the way that I think the supertype should. And this was the keynote at UPSLA was actually published a year later. I also talked in that paper about the relationship of subtypes to polymorphism. On the top line I have the CLU mechanism where I talked about the operations. On the bottom line I show how you could have done it with a type hierarchy. I actually think the type hierarchy method is better. But notice that in either case there's got to be a semantic part to it as well as syntactic part. You have to be able to, in the one hand, it's not just that T has equals, T has to have an equality relation, right? And it's not just that, you know, S is a subtype of T, but it actually has to behave like T. But the proofs happen at different times, and that's why I think maybe the subtype mechanism is better, because you define the subtype once and you prove it then, whereas the other kind of proof would have to happen every time you instantiate. Okay, what was interesting about this paper was it turned into something called the Liskov substitution principle. And this was not a name I invented. I didn't even know about it for many years. And then I think what happened is someone sent me an email and they said, can you explain this thing about the Liskov substitution principle? And I discovered that there was there was chat on the internet. It's still going on. It's called LSP nowadays. It's actually, though, very important for object-oriented programming because it's a sort of a basic principle. And later on with Jeanette Wing, I formalized it to make it precise. Okay, so that's pretty much it. Okay, here's the thing that was so stunning to me. I really hadn't been thinking about it, and when I started to think about it, I realized that the world had changed from the time I did that work to now. And in fact, my husband, who was following what was going on the internet about the time I got the Turing Award, and he was looking every day, there was more stuff, came across a quote from somebody who said, well, what's she getting that award for? Everybody knows this. And I mean, that just shows you how the world had changed. And so it's amazing. I mean, really amazing. On the other hand, you know, things are not that great. Yeah, this is how they're done, but, you know, we still have a software crisis. We still don't know how to build programs all that well. These techniques help, but, you know, a lot more is left to do. So I just wanted to conclude with a few challenges. This is not intended to be everything that one might do research on, and mostly I focused here on systems area, programming languages. It's striking that there hasn't been much progress in abstraction since data abstraction. I've been waiting for that new thing. Now maybe MapReduce is an example of something that's coming along that's new. You know, some of the stuff in patterns, there are some abstraction mechanisms there that are interesting, but by and large there hasn't been much. And maybe that's what it is. You know, or maybe somebody will have a breakthrough and we'll see a better way of doing things, and that will improve the programming process. Massively parallel computers are the problem today. The real problem is how do you implement programs that run on them? We can all see how we can use a small number of processors, but you know, can we use 100 processors? Can we use 1,000 processors? You can use them if you have data parallel. If a data parallel structure works in your problem, but you know, could I implement a database on such a machine? So we're not going to be able to use these machines unless we can figure out how to program them. This may be just the right answer, by the way. I mean, just because Moore's law is running out of steam doesn't mean that Intel has to sell us computers with thousands of processors in them. It's a kind of a gap there. But on the other hand, I think this is a very important problem, and it would be nice. We haven't made much progress in parallel programming in all these years, and so now's a good time to look at it again. It's clearly this is an area that's a very rich source of problems for machine architects. It's a very rich source of problems for people who work in operating systems, but the real question is the programming languages or the programming paradigms. How are we going to use those machines? That's going to be the crux of the problem. The other thing I think is really interesting is the internet as a computer. This is more in the area that I'm in. We can see this happening with cloud computing. Storage and computation are moving online, but there's just a host of problems out there. Nothing is really very well defined. The semantics of running a program on the cloud, when something goes wrong, what does it exactly mean? The same is true for storage. The storage is not all that well defined. The semantics are not necessarily what you want. And so there's a whole bunch of problems that need to be solved to make that a reality. And I don't think this is entirely a systems problem. There could be a programming language problem there too. Maybe we'd like to actually write programs that run on the cloud and think of them as being sort of distributed programs with components that can be put in different places. It's kind of odd to me that programming languages today only give you the ability to write something that runs on one machine, and then you link up your pieces. I'm talking now about distributed computing by going to some other mechanism, .NET or something like that. Maybe we really could have a programming language where you write your whole distributed program as a program in that language, and that might be a good thing to look into. So anyway, there's many problems left. I know I'm talking to many students here, so there's lots of research to do, and that's the end. Thank you. I'd be happy to answer questions if there's, yes.
As a programming language designer, what do you think about the programming languages that a lot of people are using today? Some of the newer things like Python, Ruby, JavaScript, which were, to some extent, some of those were designed by accident, or certainly a lot of them designed by people who didn't have a background in designing languages, but have become very popular and in some cases intractable. Like, you can't avoid JavaScript if you're doing stuff on the web.
Yeah.
No matter how much you love it or hate it, it's just there, and that's what we have to deal with.
Yeah, I think it's very sad. I don't know, and I guess what happened is that the programming language people were ignoring this audience, and so therefore amateurs stepped in to fill in the gap, and we're all paying for it. So I had a sort of a horrifying experience by proxy, I have to say, because it was one of my graduate students who discovered this. But we were looking at a web server, and this web server had confidential information that it was in charge of, and it was just kept up there in the global storage, and all the code could access it, and it was just who could say that there was any security in this code? I mean, it's like it's back to the bad old days. So I honestly have not been following the programming language world. My friends tell me that Python is gradually turning into a pretty good language. They tell me that Ruby has iterators. I've gotten kind of interested, so I was thinking maybe I'd start looking at them. But I do think there's, in some sense, the world of the professional programmer. I mean, we may not build our programs in Java because we're at too low a level and the performance matters too much, but we use the principles. And then there's this other world where an awful lot of code is being written, and it's being written in languages that aren't very good by people who don't know what they're doing, and it's really a problem. And there's a tremendous, people don't like strongly typed languages, and maybe that's because the strongly typed languages have too much syntax in them. Because it isn't necessary to have types on all the variables. You need types on the interfaces. And so maybe, I think it'd be good for programming language people to pay attention to this, and maybe something better can come along and, will start to improve the situation. I also think the systems people are to blame, because especially when you look at the browser side, the way those, those are fundamentally operating systems, but they're terrible operating systems. So, that's another place where work needs to be done.
So we should take questions from the remote audience first, because that link will...
Yeah, sure.
So are there any questions from UNC or NCSU?
I'd be happy to take questions from the remote audience if somebody has a question.
Barbara?
Yes.
Can you say anything about the decisions you made in choosing the parameter passing conventions in CLU, like call by value or call by reference? What was your thinking about that? I couldn't tell from the description.
We used to refer to it as call by object. It's really exactly what Java has. If you ignore the fact that Java has integers and they're treated differently, if you just think about the objects and you're always passing pointers. It was a decision we made very early. I never liked call by reference. I really didn't like call by name.
How does it differ from call by reference?
Call by reference, if you remember, in C, for example, you can actually have a pointer in the stack, up to the stack, and then the idea is you can assign to that variable and it'll assign, So really CLU is an object-oriented language in the sense that all the objects are sitting in the heap. The program variables all point to those objects, and when you call a procedure, you simply pass those pointers along. So it really is, I'm not sure about the technical term at this point, whether call by reference now means that, but heap, variables, that was sort of the view. Yeah. Nothing was by accident in CLU. There was a lot of, we thought about everything, so everything was thought about. And for example, we never actually implemented, but we intended to implement checking of uninitialized variables. So we decided that if you think about, you have a declaration, so you create a new variable, is it required by the language that you immediately assign to it, so it's never uninitialized, or not? Okay, this is a language design decision. And our design decision was that we would not require it to be initialized, because if you do that, what you do is you end up sometimes with phony initializations where the person just wasn't ready to initialize. You could initialize if you wanted, but you didn't have to. And then by simple program analysis, you can mostly figure out whether when a variable is used, it has been initialized. And so in the few cases that were left, we would do runtime checking. Okay, so that's a very reasonable way of handling the problem, where you catch the errors when they exist, but it really has no cost most of the time, because most of the time through compiler analysis you can figure out that no checking was needed. That's just an example of the kind of stuff we did think about. I think there was a question over here.
Yeah, I think much of the discussion on abstractions was on data structures. Have you followed much about what's going on in abstractions for behavior, like state machines, activity diagrams, and workflows? In the programming language world, we use them to learn how to program, but in the operating systems and middleware area, these abstractions seem to be becoming an integral part of the application server, if you will.
So I have to say I have not paid very much attention to workflows. I'm a little familiar with them, but I haven't been paying a lot of attention. So, yeah.
I have another question about iterators. So in your example, you had set and there's no order.
Right.
Right. But sometimes you do want that order preserved, like if you iterate through a stack or you iterate through a sorted list.
Yep.
But there doesn't seem to be, I couldn't figure out how you would actually enforce that in the implementation of.
Okay, so in a programming language, programming language doesn't capture semantics. All a programming language does is type checking does a very simple part of correctness checking. You can capture some of what's needed to ensure your program is correct by having strong typing and type checking. But to really get a correct program, you have to have specifications. And it's in the specification that this information would be given. So for example, the specification for the members operation for set would say maybe arbitrary order, whereas the specification for a stack would probably say from earliest to latest. And you would put this into the specification, and then the implementation would only be correct if you could prove that it matched the specification, and the using code could then rely on the specification. One thing that's interesting about iterators, by the way, is that sometimes with an iterator, it's okay if the code in the loop modifies the element being iterated over, and sometimes it's not okay. And so part of the specification for the iterator has to say whether it's okay or not. So the reason I'm having no trouble answering your question is because this is the kind of stuff I taught in my course. I developed a course at MIT about programming methodology and software engineering, and I taught the kids about specifications, about how to specify all the different kinds of abstraction mechanisms. I also taught them all about how to reason about the correctness of data abstractions, including what rep invariants were, what abstraction functions were, and I even had them implementing rep invariants and abstraction functions because these are not only really good for increasing their understanding, but they're also very useful when you're debugging because the rep invariant you can check in your test suite to make sure it's always holding, and the abstraction function you can use to see whether the object looks like what you think it's supposed to look like at this particular moment in time. I always worked with informal specifications, so I developed a way of writing informal specifications with a sort of a syntax that's not that dissimilar from some of the stuff you see in Java where you put in your comments. Yes?
When you explored some of the ideas relating to inheritance, where did you fall on the idea of multiple inheritance, like in C++, or not multiple inheritance? I know that might start a flame war.
Yeah, no, I didn't pay an awful lot of attention to that. I do think that some of it probably came from the fact that they were trying to do two different things with one mechanism. So you might use inheritance because you could borrow from this implementation, but the behavior you were trying to get was this other thing over there. But I don't really have a position on this. I was sort of not focused on it. Yeah. Yes?
You've mentioned debugging now twice. It seems like there's this kind of meme going around in some of the programming languages communities where debugging is considered bad or a crutch. I've actually heard it. I'm just kind of curious what your thoughts in general on debugging.
Well, Dijkstra always told you should write programs that were correct from the day one, and you didn't have to test them. I'm pragmatic. You try to write correct programs, but you have to test them, and if they have errors in them, so it's very important. So another thing I teach in that course doesn't exist anymore, but that I used to teach in that course, was how to develop good test suites. Because getting a good test suite in place is a very important part of the process for making sure your programs work right, but if they got errors in them, you got to debug them. So I don't think it's a matter of, I don't think there's a philosophy here. I think it's, it's how the world is. We should be so lucky that we could write programs that were correct without, on the first try. So. Yes?
Were there any moments where you took ideas from other engineering principles and you said, okay, wait a moment, civil engineers are doing this thing, perhaps we should do something like them to make our engineering process more as robust and as reliable as them?
I can't say I ever took anything from another engineering discipline, except that when I started the work on programming methodology and modularity, I kind of envied the electrical engineers because I felt that they had a much easier job than we did, since you have to build your systems out of components. Those components are connected by wires, and this kind of forces a natural modularity on you, whereas in the software domain it was so plastic, you could do anything, and so we had to invent all the principles that sort of got us to where we are today. But no, I'm not an engineer by training. I came out of math and then I went into computer science. I don't know a tremendous amount about other engineering disciplines. Yes?
So basically, I have questions about the main design goal. Because the goal is to show the concept of abstract data type, object programming. You were actually thinking that Glue might be adopted by a lot of people. That's what I thought is later, Java is it took so much from Glue, but it's one area that used. But nowadays, people don't really program.
That's right. So the question was, did I think of CLU as being a language that would be then produced commercially? And I was really in it for the research, so I wasn't thinking about that. But when I finished the work on CLU, which was around the late 70s, I did think about it a bit. And the world was different then. So today, you could take something like the CLU compiler, you could put it online as freeware, and you might very well have adopters. I mean, that's what's sort of going on. In those days, though, the only way you could have a language that would be commercially viable would be for it to be coming out of a company that provided support and so forth. So I would have had to stop doing research and have formed a company, and it just was not the thing that I decided. It was like there was a big path, a big fork in the road at that point, and I decided not to go in that direction, but instead to go into that distributed computing direction. It's, you know, it was definitely a decision, and it's not, you know, I can't say I regret it, but in fact, you know, it would have been nice to see CLU get out there and be more used, but it's very nice now, though, that the ideas have, in fact, moved into mainstream languages. Yes?
When you find yourself writing code now, what language?
You know, the way I survive as a faculty member is I don't write code. That's what graduate students are for. We mostly implement using C and C++. The reason is that we're always building platforms that we want other people to build applications on top of, and performance matters so much for us that we have to sort of pay attention to that. I hope my students are writing good code. It used to be the case that they all taught my course, and so they'd all had rigorous training in modular construction. And as you know, you can write perfectly nice programs in C and C++. There's not any, you have to be disciplined, but you can do it. But yeah. So.
Thank you.
You're welcome.